with sharing my screen, so just give me a moment. Okay, so everybody should now be able to see my shell screen. So if you guys could all start by firing up the shell that you have on your system. So if you're on Windows, that would be git bash, or if you're on Linux, that would be firing up the terminal like I have done here. So once you've got that open, if you could just test out the flags on Zoom and show me that you've all done that with the green sticky, that would be really great. Okay, so once everybody's got bash out and open up and running, if you could get a green tick. Okay, that's brilliant. I think we've almost got everybody. Manuel, have you managed to get your bash shell up and running? Doug, would you be able to jump in and just help Manuel get started? Okay, great, thank you. Okay, brilliant. So it looks like everybody's got their shell up and running there. Okay, so as Alex said, the first lesson of this morning is using the Unix shell. And just to kind of follow on from her words about the motivation for learning shell, basically, we're all very comfortable interacting with our laptops or other devices using a graphical user interface, and that can be really comfortable for us. But it potentially runs into problems when we're doing our research, because when we're doing lots of repetitive tasks, there's a potential for error. And also it can be really slow adopting a point and click approach if we want to do lots of perhaps complex calculations over and over again. So what the shell offers us is a completely text-based way of interacting with our file system. And that means that we can tackle some of these repetitive tasks and automate them and complete them very quickly. Learning shell can also be really useful because in some contexts it can be the only option available to us if we want to interact with a remote computer. So for example, a high performance computing system or a supercomputer. And what we're going to try and do this morning is build up a set of vocabulary where we use the shell to interact with our file system and work towards automating some of those tasks. So the first step towards doing that is navigating files and directories. So the first thing we want to learn how to do is how to move around our computer, see what files and directories we've got, and also be able to open a particular file or directory on our system. So now that we've all fired up our shell, the first thing that you should see on there is the shell prompt, which is this $sign here that I've highlighted. So the presence of the shell prompt indicates that shell's waiting for input from us. Okay, so the first command that we're going to try out is pwd, and that stands for print working directory. And that's going to tell us where we are in our file system. So what folder are we in on our computer? So I type pwd into the shell, and once I've done that, I hit return to run the command. And as soon as I do that, I get some output back to the shell. And what it's telling me is what folder I'm in on my computer. And we can break this down a little bit more by having a look at the structure of the file system on my computer. So I'm just going to print the output. I'm going to print the contents of a file to my shell screen to show you a diagram of my file system. So this diagram shows the file system on the laptop that I'm using to go through this lesson. And so if we break down the output from the print working directory command, what we're seeing is that our file system is hierarchical. At the top of the file system, we've got the root directory, which is indicated by a slash. And then underneath the root directory, we've got a set of subfolders, and within the subfolder users, we've got a folder for mjk_igkk2, which is my username, but we've also got a number of other users who, in this case, are fictitious. So if we break down this file, the output from pwd, what we're seeing is that we've got the slash, which is the root directory at the beginning, and then we have a subfolder, which is users, and then I'm in this folder mjk_igkk2, which is my home folder. And the default behavior of shell, normally when it opens up, is to take us to our home directory. Okay. So that's the print working directory command. The first command that we're going to try for ourselves is list. So once we know where we are within our file system, we can have a look at the contents of our folder using the list command. So ls stands for list, and the default behavior of list, once we hit return, is to show us the contents of our current working directory. So when we run the list command, we see a list of all the folders in our current folder and all the files that are there. So you'll see that the output here is color coded. All of the folders here are in blue. Any programs are in red, and any normal simple files are in black. So for example, resources.txt is colored in black.
Can I just quickly interrupt? Sorry, Camilla. Please make sure that you are following and typing along with Camilla, and make sure that you're typing all the commands that Camilla is doing, okay? They might look slightly different on your machine because you will have a different set of files and directories, but I think, is that the idea, Camilla? You want them to type these commands as well along with you?
Yes, so as Alex explained at the beginning, what we're trying to do here is I will be coding on the screen, and if you guys could have your shell up and running and be following along exactly as I'm doing. So if at any point I'm going too fast, please let us know through Zoom. So the idea is for you guys to type exactly what I'm typing and see the output as it appears, and see exactly how the commands that we use behave on your machine. So the first command that we're trying is the list command. So ls stands for list. And what we're doing here is finding out what the contents of our current directory is. When we run the list command, what we see is a list of all the subfolders in my current folder and any files that we have there. And as I was saying, the output is color coded in my terminal. But if it's not color coded in your terminal, what we can do is use something called an option. Now, an option is going to modify the default behavior of any command that we're using. So we can use the -f option to modify the behavior of the list command. So if we type ls-f and then run that by hitting return, we can see that the default behavior of list has been modified, and it's added a set of markup to the output. So for every folder, a slash has been added at the end of the folder. Any programs have been marked with a star, and any normal files like resources.txt are unmodified. So it's helpful at this point to just pause and have a careful look at the anatomy of a shell command. So we've mentioned so far two commands that we've used. We've used pwd and we've used list. Now, the default behavior of list was to show us the contents of the folder that we're in at the moment. But what we can do is we might be interested in the contents of another folder. So we can specify an argument that defines which folder we want to find out about. So we can type list-f and then slash, and slash, as we mentioned previously, represents the root directory in our file system. So what we're doing here is we're giving the shell three components. We're giving the command, which is list. We're giving an option, and options are used to modify the default behavior of a command. And we're giving an argument, and the argument specifies what the command is going to act upon. And so here we're saying we want to find out about the contents of our root directory. And our root directory was that folder right at the top of our file system hierarchy. So once we've got these three components of command, option, and argument, we can run that by hitting return. So when we do that, you can see that the output now is very different from what we had before. So our first output was showing us the contents of my home directory. You remember that that was users mjk igkk2. What we're seeing now is similar, but the contents is really different. And that's because we've asked List to tell us about the contents of my root directory, which is right at the top of my file system hierarchy. So we've got different folders like applications, bin, data, and so on. Okay, so that's the overall anatomy of a shell command. So as I mentioned, we've got the command list, and then we've got -f, and then we've got which folder we're interested in finding out about. Now, we've so far looked at two commands, pwd and list. So as we acquire more vocabulary for interacting with the shell, how do we find out what options a command has got and what arguments it needs to run it correctly? So there are two ways that we can do that. The first one I'm going to demonstrate, called the manual pages, will work on my Mac. And the second one will only work on Git Bash and on Linux. So we'll try the method which is going to work on Mac first. Okay, so if we're learning the list command for the first time, and we want to find out what options it takes and what arguments it takes, we can get that information using the command man. So I'm going to type man on the command line. I'm going to type man list. And I run that by hitting the return key. And as soon as I do that, it launches a help page within the terminal. And we can navigate this help page using the spacebar and the up and down keys. So we can dissect this page a little bit more to show how we would use this in the wild if we're learning new commands. So the first piece of information that we've got at the top of the help page is the name of the command and a brief description of what it does. So ls list lists our directory contents. So that's what we expect. And then we've got a synopsis of how to use the command. So we've got the command name here, and then we've got a breakdown of all the different options that list can take. And so far, we've just used one option, which was -F. And if you remember, that modified the default behavior of list. So we had our initial output, and then the -F option added all that markup to tell us what was a file and what was a directory. So there are many more options than the F option that we've seen so far. Now, these square brackets tell us that all of these options are optional. And secondly, we've got our argument. So here we're seeing the square brackets again, and square brackets always mean optional. So it's telling us that list can take a file or a folder as an argument. So to break this down, we've got our command and then a list of all of the allowed options and then all of the allowed arguments. And then if we navigate through the help system, we can see a listing of each argument and a description of what it does. So if you pull up the man page for list and then navigate through by pressing the space bar, we can see here halfway down we've got the description of -F, and it tells us exactly what that option does. And if we continue to navigate down, we come to the end of the help page. And once we're there, if we want to exit the help page, we can hit Q. Okay, so that's one method of getting help to learn about learn more about a particular command that you're using. The other option, which works on Linux and on Windows, hang on, will be the help option. So we can type the name of the command and then -- help, and that should launch in your terminal a very similar page to what we saw with man. But it's not actually a valid command in Mac terminal, so it's telling me that it's an illegal option. I can just see a number of messages in the chat, so I'm just going to check that everything's okay.
Yes, I was going to ask you to repeat how to get to the man page or the manual page for a command, and also how to exit from a man page.
Oh, okay.
Because
yeah,
people got stuck. Yeah, man pages are a bit weird.
So it's a shame that I can't demonstrate it for you, but there's a difference between list help and man list. So if you use the list help command, the help page will be, the help text will be pasted into the shell, and you don't have any difficulties around navigating the page that comes up. If you use man list, we type the command man followed by so we type man followed by the name of the command that we want to find more about. We hit return. As soon as we do that, the help page effectively takes over our terminal. And to navigate through, you'll see at the bottom of the screen, you've got this colon. And if you can navigate through the help page using the space bar. And once you come to the end of the paging, or at any point, you can hit Q for quit, and it will exit the help page, and you'll be able to come out of it. So I'm just taking a moment to check the chat to see how everyone's doing. So yeah, as we mentioned, man should work on any system, and the help command won't work on Mac.
We have some problems with someone on Windows. Simone can't run man, doesn't work for him, but the -- help command does work.
Okay,
and I think I've seen this problem with those. Is it git bash that you are using on Windows, or is it the shell that comes with Windows 10? Git bash. I think there was a comment somewhere that it doesn't really work exactly like shell. So shell is a Unix thing, and these things for Windows are trying, it's like emulations of a shell, so it doesn't work 100% the same. I'll try and find a link about the man page and paste it into the chat and see how it. I'll try and find how it works on Windows.
Okay, so to recap, we've tried 2 commands so far, pwd, where we found out where we are on our file system, and we've tried our second command, list, and we've used options with it, and we've tried an argument with it. So what that's allowed us to do is to find out what the contents of our home directory is, which is the directory that we land in when we first power up our shell. We've been able to see the contents of the root directory in the file system. And we've been able to look at the help pages to find out more about what a command does, what its options are, and what its arguments are. So what about if we want to find out more about the contents of our file system, not just be restricted to looking at the home directory or the root directory? So let's say, for example, I wanted to find out what's on my desktop. So we can repeat the same process that we've used so far. So I'm going to use the list command. So I'm typing ls. I'm going to use the -f option again, because I like that output where it tells me what's a file and what's a directory. And then I'm going to type the name of the folder that I'm interested in finding about, which is the desktop. So once I've got those 3 elements, the command, the options, and the folder name that I'm interested in finding out about, I can hit return and run that. And again, what I get back to the terminal is output, which is telling me what's the contents of my desktop. And at the moment, my desktop is very clear. So there's only two things on my desktop at the moment. I've got the data shell directory, which are the files for this lesson, and the original zip file that folder came from. So we've looked at the contents of a directory, but what if we want to move to a particular folder location? You know, potentially we want to do some actions in that folder later on. So we've seen what's in the desktop folder, but what about if we want to change our directory, change our location to that directory? So that leads us on to our next command, which is the cd command, which is short for change directory. So I can move into this desktop folder by using the command cd followed by the name of the folder that I want to go to. So I'm typing cd desktop and then I hit return. When I do that, I don't get any output to the shell. So far the commands that we've used have produced output, but that's not always the case. And so sometimes we need to use additional commands to reassure ourselves that we've achieved what we set out to. So once I've changed the directory to desktop, I can use the list command to verify that I have actually moved to my desktop by looking at the contents, or I can use that print working directory command, pwd, to tell me what my location is. And again, we're seeing that I'm in users, mjk, desktop, and that's my location now. Okay, so we've seen that in that desktop folder, I've got a subfolder, which is the data shell. So what if I want to move into that data shell folder? Well, I can repeat the same process. So I can continue moving down this file system hierarchy by typing cd and then data shell. So I type cd data shell, and once I've done that, I can hit return and then use pwd again to verify that I'm in the data shell directory. So once, if you guys could follow along with me and navigate to the data shell directory, and once you've got into the data shell directory, if you could give me a green sticky to let me know that you've got there, that would be great.
So we have a question on the chat from Matthias. Is this something to download? So Camilla, if you can just go through that again, please.
I can't, hang on a second.
The answer is yes. Yes, you do need some data that we will be working with in this lesson.
Hang on, I can't find, I've got too many windows and I can't find the chat window. Bear with me. Alex, would you mind just reading the question for me? Because I don't have easy access to the chat window at the moment.
Yeah, so the question is, it's about the data shell file. So Doug has just put a link on chat where to download the data that we will be working with.
Yes, so we're going to be working with a folder of data files called the data shell folder, and that's available from the course material page. And if you could download that to your desktop and unpack it, that would be great.
Okay, so is that a green sticky for if everyone's got the data shell unzipped on their desktop or wherever they want to, as long as they can find and navigate to it later on, put a green sticky on. I'm just going to clear everything now, all the stickies. And now, please, once you've got the data shell file downloaded and extracted in a convenient location, put a green sticky, a green tick in Zoom, please.
Hi, I'm sorry, can I interrupt for a second?
Of course.
Yes.
Yeah, so I went to like, on my desktop, I went to like another file, not the data shell. And how do I get back to like the desktop?
Okay, that'll be the next command that we'll do. So just hang in there. If we just wait till everybody's got the data shell directory, I'll explain to you exactly how to get out of there. Don't panic.
Okay.
It's cd ... to go one step up. Just a quick fix to go back to desktop. Let us know if that's working.
It says command not found.
cd and then blank
Space.
and then dot, yeah, space and then dot.
Oh, okay. I think it works
Yeah.
now.
Are you now
No,
in desktop?
I'm the same as well.
Yeah.
Okay, so just pwd to print your working directory. Okay, so there was another question from someone else.
Yeah, mine says file not found or directory not found, but I'm just downloading the data shell.
Mm-hmm.
So yeah, if everybody could download, we'll pause for a moment, and if everybody could download the data shell file and then unpack it on their desktop, and if you do that the way that you normally would through the file explorer, that's absolutely fine. As long as you download that zip file to your desktop folder and unpack it in that location, it should be fine. So once everybody's got a data shell folder, if you could just show me a green sticky.
Okay, so we have another problem. So Emil seems to have a problem with, Emil, have you downloaded the file, the zip file, and did you put it on the desktop?
Yes.
Have you saved it on desktop?
Yes.
And then you extracted the zip file.
No. Okay.
So extract that from your file explorer.
Again, it gives error.
It gives you an error when you try to extract.
Yes. For data shell zip.
What does the error say? Okay, so I'm going to send you and Doug into a breakout room, maybe. See,
Sure.
let me see. Oh, actually, I can't. Doug, you're the host.
Right. Okay. Shall I break out rooms? I'll make you the host.
Okay, make me the host, and I'll make the rooms for you.
Yeah, I can't remember how to make breakout rooms.
Okay,
so.
That's okay. I'll do it. Okay, so I'll just assign Doug and Emil. Okay, everyone else stay in the main room. Okay, so is everyone else okay? So everyone else, Simone, how about you? We don't have a green sticky from you. Yeah, all good? Okay.
Okay, so I'll pick up where we left off. So if you could navigate to your home directory. So we can use the cd command to get back to our home directory. So if we type cd without any argument whatsoever, its default behavior is to take us back to our home directory. And from there, we can repeat that step of moving into our desktop folder. So once we're in our home directory, So I'm in MJK IGKK2. I can type CD and then desktop. And once I do that, that takes me to my desktop folder, and I can use ls-f to see the contents of that folder. And we can see that I've downloaded the datashell.zip and I've unpacked it, and I've got my datashell directory there. If I want to go down another level in this file hierarchy, I can type cd datashell, hit return, and once I do that, we can see that I've navigated to my datashell folder. But I think someone mentioned that they accidentally went into the wrong directory in their desktop folder. So what do you do if you want to move back up that file hierarchy? So you can, as Alex explained, we can use cd ... And in this case, ... is a shorthand for the directory above our current location in the file hierarchy. So if we run that command, that takes us back one level in the file hierarchy, and we can see that we're now back in our desktop folder. Now, how can we move easily between different folder locations that we want to be working in? So what we've seen there is we've gone into the desktop folder, we've gone down into DataShell, and we've used the ... shorthand to move back up that file hierarchy. Now, if we want a quick way of moving back to our home directory, we can use a cd command without any argument at all. So if we type cd on the command line and then hit return, that takes us back to our home directory. But what if we want to move back to the DataShell directory on the desktop where we were before? We perhaps want to start doing some work in that folder. So far, what we've been doing is we've been in a folder, and then we've had a look at the contents of that folder, and we've seen subfolders listed there. And then we've used the cd command to change our location into a subfolder. So for example, in the home directory, we've listed the contents, and you can see my desktop folder is here. And then the next step that we've done is cd desktop. Now, this is what's known as a relative file path. So what we've been doing is we've been specifying the folder that we want to go into relative to our current location. And you'll notice there's no slash at the front of this folder specification. Now, there's an alternative way that we can specify the location of a folder on our file system, and that's using an absolute path. So instead of typing a subfolder within our current location, we can specify a location relative to that root directory that we saw right at the beginning. So we can specify our location from the root directory at the top of our file system. So instead of typing cd desktop, you can use a different approach. We can type / which stands for our root directory, and then we can type users, and then my username, which is mjkigkk2 / desktop. So we've got two possible alternatives we can use to move into the desktop folder. I can use this absolute path where I'm typing cd users mjkigkk2 desktop. That's one option. And if I do that, that takes me back to the desktop folder, and I can confirm that by typing pwd. And that's an alternative approach to typing cd desktop, which was our relative path, and our relative path was specified with respect to our current location. So we've moved back to our desktop, and we can, once we're in our desktop location, we're going to run through that process of moving back to our home directory one more time. But this time we're going to use an absolute path to practice what we've just learned there. So previously, when we wanted to jump back from our desktop to our home directory, we typed cd without any arguments. But we can test out two different ways of moving back to we can test out another way of moving back to our home directory. So we can specify the absolute path this time by typing cd users and then mjkigkk2 IGKK2. And if we hit return, that will take me back to the location of my home directory. And once I do that and type pwd, I can confirm that I'm back to my home directory.
So has
Okay.
everyone managed to follow this? Has everyone managed to get back to their home directory? Obviously, their usernames will be different from Camilla's. Okay, because some green stick is showing off. Maybe put a green tick if you've managed to come back to your home directory using these absolute paths. So ML is in the breakout room, so it's just Simone now we are missing.
Okay, so before we spend 5 minutes doing some exercises together, I just want to take a closer look at how we're writing the location of our home directory. So you remember that the home directory was the first location that we came to when we opened our shell. Now, my home directory is called users mjk igkk2, and as Alex mentioned, yours will look slightly different because your username will be different from mine. So it might be your name, it might be your university username. And in the last step that we did, we used cd users mjk igkk2 to go back to my home directory. But there's a useful symbol that we ought to touch upon before we move on, and that's the tilde symbol. So the tilde symbol on your keyboard is used as a shorthand within Shell to stand for this the location of your home directory. So if we're specifying a folder location, a third way of specifying the desktop folder is by using the tilde symbol to stand for the home directory part of the path. So instead of typing users mjk igkk2 desktop, we can type tilde / desktop, and that's equivalent to users mjk igkk2 and desktop. So we've got effectively, when we're in our home directory, that gives us 3 different options about how we can move to that desktop folder. We can use our relative path, cd desktop, from where we are now. We can use our absolute path from the root directory, so cd users mjk igkk2 and then desktop. But then we have this third option where we use the tilde symbol to represent our home directory. And so we can use that to navigate to our desktop as well. And we'll see that tilde symbol being used to represent the home directory as we move on with the course. So I'll just demonstrate that that's another alternative way to move to the desktop. So we can verify that we're in our desktop folder. And if we'd like to move back to our home directory, we can type cd without any arguments, like we've seen before, or we can type cd tilde and standing for our home directory, and that will move us back to our home directory again. Okay, so I think it would be useful to take a moment to put some of this to the test, and we can go through some of the exercises in the first episode. Just give me a moment to share the course notes screen for a second.
Can I just quickly ask, is ML, I know ML and Doug are back, is everything okay?
I'm here,
Following.
thank you.
Good, good. Are you following now?
Yes.
Okay, brilliant. Cheers.
Okay, so we're just going to take 5 minutes to go through some of the exercises in the navigating files and folders episode. So the first exercise that we're going to go through is exploring, there's 4 exercises in this chapter. So we're going to look at exploring more LS flags, listing in reverse chronological order, and then there's 2 exercises towards the end of the course notes. So I'll just paste the link into the chat. And we're going to go through the exercises that are listed in the course notes. So the first exercise is to try out some of the other options that are available with the list command. So if you guys would like to try out the -L and -H commands and share with us, if someone would like to test those out and then report back to us what they do. So I'm going to paste the question into the chat, and if you guys could test out the list command on your home directory with these new options that we haven't tried yet, and if someone would like to volunteer and report back what they do. Or paste into the chat if you feel more comfortable that way.
Camilla, do you think you can share your screen and maybe show the exercises?
Yeah. So this is the exercise that we're looking at. I don't think I can share my terminal at the same time, can I? That's the problem. So once you've tried the -L and -H option, if you could paste answers into the chat and let me know what they did.
So we have a couple of questions in the chat. So you need to type, Emil, you need to type the command as ls -l, okay, not just the -l. So the command is ls, and the -l is a parameter that slightly modifies the output of that command. So changes what that command gives you.
So one person has reported back. So yes, that's absolutely correct. So let's have a go together. I'm going to stop sharing the course notes screen and go back to the terminal to try this myself. So if we type ls-l, so let's do a basic ls. If we do a basic ls, we get simple listing of folders and files. But if we type ls-l, we see.
No, Camilla, you're not sharing your screen.
Oh, sorry. Okay, hang on. Okay, so if we use a simple ls command, we see the listing of folders and files in my home directory. But if we add the ls-l option, then we see a much richer output. And as somebody mentioned in the chat, yes, what we're seeing is the sort of file creation dates and permissions and the owner and all of this sort of stuff, and file sizes, I think, as well. So -L gives us a much richer output. And if we use the -H command, ls-l and -H together, we get a slightly modified output. So the file size output has been modified so that it's a bit more human friendly in terms of its formatting of the file sizes. So to try another another few options to the list command. The question asks us in the exercise, by default, list lists the contents of a directory in alphabetical order. The command list -t lists items by the time of last change instead of alphabetical. The command list -r lists the contents of a directory in reverse order. Which file is displayed last when you combine -t and -r? So yes, if you could try that one out. So if I type list -t, which is going to give me the times of the last change, it's going to order my files in terms of time of last change, and -r, which is going to reverse the output. What do we think the output of that command is going to be? If you could let me know in the chat what you think. Okay, so do we think this is, yes. Okay, so one person said it will give the earliest file displayed last. Okay, anybody else? Okay, so I'm going to try that out. Hang on. So to verify, I want to use multiple options together, and it's worth mentioning here that we can use multiple options together in two different ways. We can type each option separately like this, or we can combine all of our options in one flag like this. So let's have a look. So what we've got is our oldest file being listed first and our youngest file being listed last. Okay. Okay, so let's try one more exercise from the episode. So if we move to the last set of exercises, absolute versus relative paths. I'm going to read the exercise questions to you because I don't think I can share my terminal and the notes at the same time. But if you have a look at your notes in your browser. So starting from users/Amanda/data, which of the following commands could Amanda use to navigate to her home directory, which is /users/Amanda. So we've got 9 different options being presented to us. So I guess if you guys could vote in the chat and let me know what your choice is. So if you could paste the number of your choice into the chat and we can see roughly what people vote for. So we're looking at the exercise, which is absolute versus relative paths.
Was everyone able to find the text of the exercise?
Okay, so the text of the exercise would be at this link. Okay, so I think I can share this one, I think, so I don't need the terminal. Okay, so we've got, can everybody see that? Am I sharing?
Yep, can see it.
Okay, great. So starting from users Amanda data, which of the following commands could Amanda use to navigate to her home directory, which is users Amanda? So the first command is going to take us to the current directory. So that means we're going to stay in the users Amanda data directory. The second command is going to take us to the root directory. So neither of those options is going to work. CD home / Amanda. Well, Amanda's home directory is not home / Amanda. It's users / Amanda. So that one won't take us to our home directory either. CD ... is going to take us up into the users directory. So we're in data at the moment. So the first ... is going to take us up one level, and the second ... is going to take us up one level again. So number 5, CD tilde. So remember that tilde was an abbreviation for our home directory. So that's a surefire way of taking you back to your home directory. Number 6, CD home. So what that will do is we're currently in the Amanda data directory. That will look for a directory called home within the data directory. So that won't work either, unfortunately. Now this one is a bit of this one's a little bit complicated, but it will take us to the home directory. So this is going to take us to tilde, which stands for the home directory, data, which is a subdirectory, and then ... is shorthand for the directory above. So that we're in data at the moment, and the ... is going to take us into the folder above that in the hierarchy. So that will take us back into the home directory. CD, we've encountered that one before. So the default behavior of CD without any arguments is to return us straight away to our home directory. And CD ... as we mentioned before, it's ... is shorthand for moving into the folder above in our hierarchy. So that will take us back into the users Amanda folder. So that will take us to home, and we can just check the solution. So yes, 7, 8, and 9 and 5 were our correct solutions. Okay, so I think it'd be useful to move on to the second lesson within the Unix course. So I'm just going to go back to sharing my terminal with you so we can carry on. So the second lesson is working with files and directories. So what we've been doing so far is we've been using the shell to move around the file system. But what we want to do now is to start doing some of those file operations that we're going to need to do in our everyday work. So things like creating files, deleting them, moving files, moving directories, and so on. So the first thing that I'm going to do is use the clear command, and the clear command will remove the current output from the shell, so I can have a clean page to start working from. For this lesson, we need to be working in the desktop data shell directory. So if we type CD for change directory, and then tilde, and remember that stands for our home directory, desktop, and then data shell. So we're typing CD tilde / desktop / data shell. We want to go into our data shell directory on the desktop. So once we hit return, we can type pwd to check where we are. And we're going to type ls-f to find out what's in data shell. And we can see we've got a couple of different subdirectories like molecules, creatures, data, writing, and so on. So what I'd like you to imagine here is that we are a PhD student who's writing their thesis. And so the first step that we're going to take is to create a directory or folder called Thesis to do our work in. And to do that, we're going to use another command called makedir, which is mkdir, which stands for make directory. And the argument to make directory is the name of the folder that we want to create. So that's Thesis. So this is going to create a new folder called Thesis in that data shell directory. So once we've written that, hit return, and then we can use list to see what's happened. So we didn't get any output to the shell. We can use list-f to verify what's happened. And we can see here that we've created a new folder called Thesis. Now we can have a look at the contents of the Thesis folder using the same command ls-f thesis, and we can see that we don't get anything returned to the shell. So that means that we've created an empty folder. Okay, so we've done our first step as a PhD student, creating our folder to hold our thesis. But the next step is for us to start a draft of our thesis document. So to do that, I'm going to navigate into the thesis folder. So I'm going to type cd thesis. So that's going to take us into the thesis directory. So if I hit return, and again, pwd to check where I am. So as you can see, I'm in the thesis folder. Once I'm in the thesis folder, the next step is for us to create that document. So to do that, we're going to use a text editor called Nano. We're going to type Nano, which is a text editor, followed by the name of the file that I want to create. So that file is thesis.txt. So as soon as we've created that, so as soon as we've written this command out, nano thesis.txt, what's going to happen when I run this command is that similar to the man page scenario, Nano is going to take over our terminal and we'll be able to use a text editor. So once we run Nano, Nano takes over our terminal and we can start using Nano as the text editor. So I'm going to write a very short quote within this file. So I'm going to say it's not publish and perish. It's, you know, collaborate and thrive. Okay. So once you've added the content to our document, what we need to do is save our file. So it's worth just taking us a moment to have a look around at what's happening on the screen with Nano. So Nano is a very helpful text editor. At the bottom of the screen, it gives us all of the shortcuts for the operations that we might want to do. So here, this caret symbol is short for the control key on your keyboard. So that means that if we want to exit Nano, we're going to type Control X. If we want to cut some text, we're going to type Control K and so on. So now that we've added our contents to the file, the next step is for us to exit and save the file. So I'm just going to check with you guys that once you've added the content, if you could give me a green sticky to let me know that you're ready to save. Okay, so I think we've got half of everyone. So I'm going to open another tab in my terminal. I'm just going to repeat that command again. Okay. Okay, so I've seen that some people have got command not found. On Windows, it's perfectly possible for you to use another text editor. So you might want to use Notepad.
So when people type Nano in their terminal, do they get a text editor? Okay, so Nano should work. The reason why we are using Nano is because it should work across all the platforms. There are various other text editors available, and as Camilla said, you can even use Notepad or some other text editor of your choice. Just don't use Word for this, Microsoft Word for these exercises, because it saves files, even though they look like text. It saves files in a different file format. It's not plain text. Okay, so it looks like Nano is working for everyone.
Okay, so once we've added our content, we need to exit the file and save it. And I'm going to do this really slowly because it's something I found a bit disconcerting when I learned to use Nano. So what we need to do is we need to type Control X. And when we do that, we get a message at the bottom of the screen which says, save modified buffer, answering no will destroy changes. So this is asking us, do we want to save our file or not? And it's asking us Y or N or Control C to cancel. So you want to type Y for yes. And as soon as you type that in, the screen changes again and it asks us to confirm the name of the file that we want to save. So if you recall, we typed nanothesis.txt at the command line, and that was the point where we chose our file name. And Nano's remembered that, and it's asking us to confirm that that's the file name we want to use. We could change it at this point, but we won't. So to confirm that file name, we hit return. And when we do that, Nano closes and we go back to the terminal. But you'll notice that again, like with the makedir command, we didn't get any output back to the shell to confirm that anything had actually happened. So we have to use those commands that we've seen before to do that. So we can type list-f. And when we do that, we can see that a new file has been created in the thesis folder. Okay. So in that step, we've created our first text file using the shell. And now we're going to try some other file operations. So we're going to see how to rename a file if we're not happy with what we've called it, and how to move and copy some files as well. So the next step that we're going to do is to move back into the data shell directory above thesis. So if you remember, the shorthand for directory above was ... So we type cd ... return, check where we are, and we're in data shell like we expected. And suddenly we realized, okay, we set out to write a thesis document, but actually we've put a quote in that text file rather than an actual thesis. So it might be sensible to rename that file thesis.txt to quote.txt. So how are we going to go about doing that? So there isn't a rename command. Instead, we're going to move the file from one location to another. So we're going to move the thesis.txt file to a new file location using a different name. So what I mean by that is I'm going to use the command move, mv, and I'm going to specify the name of the file that I want to move. And so that's the file in thesis. So thesis.txt. And I want to rename that file. So I'm going to move it to a different location in the same folder. So I'm going to move it to thesis, and I'm going to call it quotes.txt. So what I'm doing here is I'm moving an existing file, thesis.txt, to a new location, but with a different name. So what we're saying here is that a renaming process is analogous to a moving of a file is analogous to renaming it. So when we do that, we hit return. And if we have a look at the contents of the data shell directory using that list command, we can see that our thesis.txt file is no longer there, and it's been replaced by the quotes.txt file. So what we've done there is by moving a file, we've effectively renamed it. Now, what if we want to duplicate a file instead of renaming it? So what we can do is, I'm just checking my location. So I'm in the data shell directory, and my quotes file is in the thesis folder at the moment. So what if I want to, first of all, move that file to a different location? We've got a quotes file in a thesis folder, which might not make sense. So what I'd like to do is move that quotes file from the data shell, from the thesis directory into the data shell directory that I'm in at the moment. So what I'm going to do is I'm going to use the move command again. I'm going to use thesis quotes.txt. So that's the file that I want to move. That's the old location. And now I need to specify the new location. So previously we mentioned that ... is a shorthand for the location above our current folder in the file system. We can also use the shorthand dots to indicate our current location in the file system. So if I want to move thesis quotes.txt into data shell, which is where I am at the moment, I can type move thesis /quotes.txt dot. And if I hit return, that will move the file to my current location. So if I type list-f, we can see that I now have a quotes file.txt within the data shell directory. And then if I have a look at the contents of thesis, that's now a completely empty folder. So
can we just quickly pause and make sure that everyone has managed to save the thesis.txt file from Nano or from another text editor if they've used a different one, and then that they managed to rename the thesis.txt to quotes.txt, and that they've managed to move the quotes.txt from the thesis folder one step up to the data shell folder.
Yeah, I kind of got lost because I couldn't get the Control X to work at the beginning. So I'm trying to save my text file. So I click like Control X and then yes, and then it shows me file name to write thesis.txt, and then like different options like get help cancel to files, DOS format, Mac format.
Oh, so you need to hit enter after that to confirm.
Oh, okay. Okay.
And that should close the Nano for you.
It did. Okay.
And saved, and then that should have saved the file within the thesis folder.
Okay.
And then you have to rename the thesis. So Camilla can show you how to do that again. So there is no rename command, but there is a move command. So you do renaming by moving files from one name to another or from one location to another.
Okay.
So would it be helpful if we recap that section?
Yes, that
Yep.
would be perfect. I'm sorry if everyone else has done it.
No, it's fine. I think it's helpful.
It's good to recap.
So let's have a look. So I've just sneakily changed to the thesis directory when no one was looking. So let me just type pwd. So I'm back in my thesis directory. So let's just go through that process of creating a thesis.txt file. So we did nano thesis.txt. I'm just going to write some short text there. So we add our contents to the thesis.txt file, and then we have to go through this kind of cycle of commands with Nano to exit and save. So we type Control X, which brings up the question of whether to save or cancel, and we type Y to save. And when it asks us about the file name, we hit return. And when we do that, Nano will exit, but we won't get any feedback to the terminal to tell us what's happened. So we have to kind of satisfy ourselves using other commands that we've done what we expected. So we can type ls-f, and that tells us that we've successfully created that thesis.txt file. But we might not do everything perfectly the first time round, so we might want to rename this file. So we've actually put a quote in the thesis.txt file, so it's more appropriate to give it a different name. But as Alex mentioned, there isn't a dedicated file renaming command. So what we do is we move the file from one name to another, but effectively one location to another. So what we can do is we can use the move command, and the arguments to the move command are move followed by the old file location or name followed by the new file location or name. So we can type thesis .text, which is the old name, followed by the new name, which is quote.text or quotes.text, I think. So what that's going to do is rename the thesis.txt file to quotes.txt. So we hit return, and then we can have a look at the contents of our folder to check what's happened. And we can see that we've got this quotes.txt file successfully. Now, we might want to, in addition to rename it, using the move command to rename files, we might want to use it to move files around our system from one folder to another. We can do that as follows. So I'm going to move back into the data shell directory. And what I'd like to show here is how we can move the quotes.txt file out of that thesis folder and into data shell where I am now. So now to do that, we need to be aware that we can use the dot symbol to represent the current location in the file system. So I'm going to use the move command. I'm going to specify that quotes file in Thesis, and I'm going to specify dot to say I want to move this old file, this file quotes.txt to a new location, dot, and dot is our current working directory, which is data shell. So once I've done that, again, we don't get output, so we need to verify for ourselves what's happened. And if we type ls-f, I can see that that quotes.txt file is in my data shell folder now. So what we've done there is we've created a file in Thesis, renamed it, and then moved it to the folder above. Now, the next operation that is useful to us is to copy a file and copy a directory. So for example, I might change my mind and decide that I do actually want a copy of this quotes.txt file in the thesis folder. So I can do that by using the cp or copy command. And it's the anatomy of this command is very similar to what we saw with move. So what we want to do is type cp quotes.txt. And I want to create a copy of that file in Thesis, but I want, instead of calling it quotes, I want to call it quotations this time. So this is similar to what we saw with move. So we've got the old file, or the file that we want to copy, and then the new file that we want to create. So before we were moving the file, this time we're copying it. So if we run that command and type ls-f, this time the quotes file, nothing has happened to it in the data shell directory. But if we look at the contents of Thesis, we can see that we've created this quotation file. And so we've copied the quotes.txt file in data shell to the Thesis directory. Now, the next thing that we'd like to do potentially, so we've looked at creating a file and moving it around, but it's potentially very useful for us to create a backup of the Thesis folder. So before I show you how to create a backup of the Thesis folder, if you could just give me a green tick to let me know if you're up to the same point as me and you've managed to copy your quotes.txt file into Thesis.
It is also break time as well. We are slightly over because we had a later start. So Camilla, you just have to make a decision whether you want to cover something else or make a or break now for teas and coffees.
It depends how people feel. So we've got two things to cover in the last part of, we've got 3 things to cover in the last part of this lesson. So we should be okay at the beginning of the next session. It might be useful for us to just take 3 minutes now, if that would be okay with everybody, to just come to a natural end of this section. Would that be all right?
Let me clear those green ticks. Okay, now, do you okay to just stay for a couple of more minutes to finish this lesson, or we can just carry on with this lesson, but would be better after the break, but it would be better to actually finish off before we go. Okay, looks like the majority wants to stay.
Okay, so there's two things that we want to do now. So we've got we've created our thesis folder and put some contents in it. But what we want to do now is create a backup. And to do that, we need to be able to create a copy of a folder. Now, we've created a copy of a file successfully, but we need to do something slightly different when we're dealing with folders. So I've become distracted and forgotten where I am. So I'm in the Data Shell folder, and I want to create a copy of that thesis folder. Now I'm going to do that using the copy command. And we saw that we used copy followed by the file that we want to copy, followed by its destination file. So we're going to use a similar pattern here. So we're going to type copy thesis and then thesis backup. That's the first thing we're going to try. We're going to try doing exactly the same way as we did the file. But if we do that, we get an error message saying thesis backup does not exist. Okay, so hang on, that's not what I expected to see. Okay, yes, that's what I expected to see. So what we're specifying here is the name of the directory we want to copy followed by its destination. And if we follow exactly the same pattern as we did using the file, then CP complains that thesis is a directory. And we need to add some additional options if you want to copy a folder. So if you want to copy a folder, we need to use the recursive flag and copy and use CP -R. And this is allowing for the fact that we're copying a folder and that the copy should be recursive. So everything that's contained inside thesis should also be included in this copying operation. So we're going to type CP-R thesis backup. So that's our old folder location and our new folder location. So once we do that and then type ls-f, we can see that our original folder thesis is still intact, but we've also created a thesis_backup folder as well. And we can have a look at the contents of that folder, and it's exactly the same as the original thesis folder. Okay, so the final thing that we ought to look at before we go for the break is how to delete a folder. And we need to be really careful here because when we're using the shell doesn't have a recycle bin. So when we delete something using the shell, we have to be absolutely 100% sure that we want to delete it. And the command that we use for that is the remove command, rm. And this command follows a similar pattern to what we've seen before. So we've got rm and then we've got the argument, which is the file we want to delete. So I would like to remove this quotes.txt file in Data Shell. So I type rm and then quotes.txt and then hit return. Now, as soon as I've done that, that file is going to be deleted. And as I mentioned, there's no recycle bin to undo that process. So you have to be really sure. So rm quotes.txt. Once we hit return, we don't get output, so we need to check for ourselves what's happened. Quotes.txt has disappeared, so it's been successfully deleted. But what if we want to delete a folder this time? So we've created a backup of that thesis folder, so let's get rid of the original. Now, again, if we type remove thesis and use the same approach as a file, again, it doesn't work as we saw with copy. We get an error message saying thesis is a directory, it can't be deleted that way. So we need to specify the -R flag, the recursive flag, to enable that deletion to go ahead. So we type rm-r thesis, and if we have a look at the contents of our folder, that thesis directory has disappeared, but our backup is still there, fortunately. Okay, so that's it for this part of the lesson before the break. I guess I'll hand over back to you, Alex.
Okay, thanks very much, Camilla. Yes, just a word of advice about the rm command. If you manage to type rm -r and then put put a slash, that will recursively delete your whole file system, because slash is the root of your file system. So use this command with caution. rm -r is a really powerful command, so it recursively deletes from whichever directory you tell it to. So if that's the root of your file system, then you will wipe your hard disk completely. Okay, so we are going to break now.
In the second part of this episode, we're going to look at the really powerful aspects of working with the shell. So in the first part of the episode, we really laid the foundations for doing that. So we covered some of the everyday file operations that we might do. So if we recap, we looked at some core commands. So we looked at the list command, which tells us the contents of our current directory. We looked at the pwd command, which tells us our current location in the file system. And we looked at using move to move a file from one location to another. So if you recall, we use move and then the old file name or location, and then the new file name and location. We saw the command copy, which had a very similar anatomy to the move command. And in both cases, we had to modify we had to use an option to modify the behavior of those commands -r if we wanted to move or copy a folder. So those are the core file operations that we need to do to navigate around. We need to be able to navigate around our file system and be able to do those core file operations of creating a file, moving them around and copying them before we're able to do the really powerful stuff of automating those repetitive tasks that we talked about at the beginning. So before I move on to looking at those elements, it'd be useful just to check that everybody's back. So if you could give me a green tick to let me know if you're here, and then we'll move on to some new material. Okay, that's great. It looks like we've got almost everybody, so I'll start to move on. So I'm going to use the clear command to clear my shell terminal.
I can't see your screen.
That's a good point. Okay. Sorry, I thought I was sharing terminal. Okay, so I'm going to use the clear command to clear my shell. And for this part of the lesson, I want to be in the molecules directory of the data shell folder. So I'm just going to use that command we saw before, pwd, to check where I am. I'm in my home directory, so I need to navigate all over again to that data shell directory on my desktop. So I'm going to use the full absolute path. So I'm going to use users mjk igkk2 and then desktop and followed by the data shell directory. If I have a look at the contents of that directory using ls-f, I can see that I've got a molecules folder in there, and this is the folder we want to be using for the next session. So if I navigate into the molecules directory, I can see that we've got a number of PDB files. PDB file is protein data bank format, which is used for specifying molecular structures. And what we want to illustrate here is the use of wildcards. So our goal in using the shell is to automate those sort of tedious, repetitive tasks that we're all faced with. And to do that, we need some mechanisms of applying commands to a large number of files in one go. And this is where wildcards come in really handy. So you might have encountered wildcards in other contexts, for example, doing literature searches. And wildcards are characters like star and the question mark character that are used as stand-ins for other characters. So, for example, if we wanted to list all of the protein data bank PDB files in this directory, we can do that by using a wildcard. Now, the star wildcard stands for 0 or more characters, whereas the question mark character stands for a single character. So we can list all of the PDB files in this directory by typing list-f and then using the wildcard star.pdb. Now, when we hit return to run this command, what the shell is going to do is going to unpack that wildcard that we use. So what it's going to do is it's going to expand it against the contents of the current directory that we're in. It's going to match that pattern to the contents of that directory and return the list of matching files and folders. Okay, so let's try that command. So if everybody could start following along with me and type list-f star.pdb. Okay, so you'll see that when we run that command, what we get back as output is a list of all the PDB files in our directory. Now, we can combine wildcards in different ways to get different results. So when we're automating those repetitive tasks later on, we might want to access subsets of files that match particular patterns. So in this case, we've managed to get a list of all PDB files, but we might want something else. We might want all files that start with the letter M, for example, or C, or that match another sort of pattern. So we can combine those characters of the question mark and star in different ways to get different results. So for example, we might want to just do our file operation on the ethane and methane files. And so we can achieve that restricted list by using a specific wildcard. So we could type ls-f and then star t question mark .pdb, and that stands for 0 or more characters followed by t, followed by one character ne.pdb. And if we run that, what happens in the shell is that pattern is expanded and matched against the contents of that folder. And the only file names that match that pattern are ethane and methane. And we can use different wildcard expressions to get different results. So for example, if we wanted just the PDB files starting with P, we could use list-f p star.pdb, and that should give us pentane and propane. And what happens is that, again, what happens in the shell is that the pattern is expanded and matched against the contents in the folder that we're working in. And what's returned to us is a list of the matching strings or the matching text. So here we get pentane.pdb returned to us and propane.pdb. And we'll see how powerful using wildcards is later on as we start to apply commands to large numbers of files. But what we've done there is effectively we've been able to apply the list command to a subset of files that match our pattern. But we could use later on. We will show how we can apply different commands to large numbers of files in a similar way.
Sorry, Camille, we just need to stop you for a second because some people are struggling. They've not managed to get into the molecules directory.
Okay.
Just yet.
Okay, so let's recap then and take that step by step. So let me clear my shell. So the first thing you often want to do when you return to your shell after working for some time is to check where you are now. So the first thing to do is to type pwd to check what your current location is. Now, my current location is molecules, but I'm going to go back to my home directory using cd so that we can go through that process of finding the molecules folder together. So I'm going to type cd. I've come back to my computer after the break, and I want to check where I am. So if I use pwd it tells me where I am in my file system. So I'm in my home directory, which is users mjk igkk2. But our data shell folder is on the desktop, and the molecules folder is in the data shell folder as a subdirectory. So we need to somehow to get there. Now, perhaps the shortest way of doing that is to type cd and then the absolute path of that molecules folder that you'll see printed here as the output of pwd. So I can type cd users and then your username, desktop, data shell, molecules. Okay, so oops, hang on, I've got no such file or directory. Why have I done that? Okay, that's because I've typed desktop wrong. Okay, so I can go back and correct that typo, and hopefully this should work this time. So if I hit return,
When I type in data shell molecules, like what you've just said, it just says no such files or directory.
have you substituted my username with yours?
Yeah, my username's ANN949.
And you know, if you type cd in your terminal and go back to your home directory.
Yep, it just comes up with ANN949 at UOB, then BM7GBHLF.
So if you type okay, so let's try an alternative way, because what you'll need to do here is substitute. So this is my home directory, and you'll need to substitute here your home directory. So let's use the symbol that we saw before instead, so that we don't have to do this manual process. So we can type another alternative we can do then is we can use the tilde symbol to represent your home directory. So that's representing this part of the path for me.
Okay. Yep.
/ and then desktop, and then the rest exactly the same.
Okay, yeah, I got desktop data shell molecules.
And when you've done cd, has it produced no output? And what do you get when you now type pwd?
PWD. Same as Una, desktop data shell molecules.
Okay, brilliant. So we've
thank
got
you.
there. No worries. Okay, so how is everybody else doing? Can I just check that we've all managed to get into molecules? You just give me a green sticky if you've got there. Okay, so if anybody hasn't got there, if you want to paste into the chat any specific issues that you're having, and hopefully we can help.
I think everyone is okay.
Okay, so let's recap.
But there is a question that it isn't very clear the difference between a star and a question mark. So if you can just recap that.
Okay, sure. So I'm just going to create a file very quickly to demonstrate this. So I'm going to use Nano to create a file called a.pdb. I'm just going to put some nonsense in the file. Control X to exit, yes to save, and return to accept the file name. Okay, so let's have a look at what we get if we type ls-f star.pdb. So if we so star stands for any number of characters. So this should match something called .pdb or a.pdb or ethane.pdb or any file name that's in there. So let's try that. So we've got it matches all the files in that directory, including the new one that I've just created, a.pdb. But the question mark, in contrast, stands for one character alone. So if I wanted to list that a.pdb, I can try list-f (?)pdb. And the only file that it returns is the one that consists of a single character followed by .pdb. Now, another thing that I could do is so ethane.pdb is got 6 characters followed by .pdb. So this should, and there are other 6 character words .pdb as well. So let's have a look for the 6 character words, and it returns cubane, ethane, octane. So the question mark stands for 1 character, whereas the star stands for any number of characters. So what we were demonstrating when we looked at the wildcards previously is that you can combine them in different ways to get the result that you want. So one way of returning ethane and methane was to combine the star character with the question mark character to restrict the results that we got returned to us. Now, why did that fail? Hang on. List star th star. Okay, hang on.
I think you should just have the 1 question mark.
Yeah, hang on. Yes, thank you. Right, so that returns ethane and methane. So what we're doing is we're using those wildcard characters to specify a subset of the files or folders that we want to use. And situations where you might want to do that are if we've got a load of data files from an assay machine, for example, and the files that we want to analyze might all end in a particular numeric code, for example. And this is a way of restricting the files that our command is going to act on. Okay, so that brings us on to the next section, which is looking at pipes and filters. And this one is really crucial. So what we want to do in this section is look at how we can build up, how we can tackle multi-step tasks using the shell. And we're going to do that using a construct called the pipe, which we'll look at in a moment. So we're going to carry on working in this molecules directory. And the question that we want to answer is which one of these molecules in this directory is the smallest. Now, if you're familiar with the PDB file format, you might know that a single atom is represented by a single line. So we can translate that question into which of these files has the smallest number of lines in it. Now, before we move on, I want to delete that a.pdb file that I created. Would somebody like to tell me how to do that in the chat? Using one of the commands that we've used previously. So how would I go about deleting that file a.pdb? Yeah, so someone's come back and said rm a.pdb. So if I have a look, that's correct. I've successfully managed to remove that file, and we can carry on. No, Matthias is specified. Yeah, please don't even joke about such things. Somebody suggested using rm-r and then the dreaded / please don't ever execute this command, as Alex explained earlier. Okay, so what we want to do is find out which of these molecules is the smallest. So which of these files has got the smallest number of lines? And we're going to meet some new commands here. So the first new command we're going to meet is WC, which stands for word count. So let's have a look at how that command works. So we've got the command and it takes an argument. So we're going to find out how many lines are in the cubane.pdb file. So we type wc cubane.pdb and then hit return. Now the output is a little bit more than I was expecting, so let's break it down slightly. So wc, the default output, it gives us the number of lines, and then the number of words, and then the number of characters. Now, I'd like to restrict this output just to the number of lines because that's what we're interested in. So remember we talked about options before, so I'm going to add the -L option, which is going to restrict the output just to the number of lines. So let's try that. So now when we run that again, we've modified the behavior of that WC command just to return the 20 lines that we're interested in. Okay, so we've looked at how to get the number of lines in a single file, but our question is which of these files is the smallest? So we need to run that word count command on all of the PDB files in this folder, not just one of them. And so this is where we rely on those trusty wildcards that we saw before. So let's try that then. So wc-l, and we're going to use star.pdb. So that star was any number of characters, including 0. And we want to run the word count command on every single PDB file in that folder. So that wildcard will get expanded and matched against the contents of our folder. So if we hit return to run that, we get a list of the PDB files in our folder. And for each one, we get the line count on the left-hand side, and we get a final line, which gives us the total number of lines across all of the files. Okay, so now visually, it's immediately obvious to us that the smallest file is methane.pdb with the 9 lines. But what if we were working with thousands and thousands of files? That might not be immediately obvious. So we might want to output this information to a file so that we can explore it further. So let's look at how to do that. So far, as we've been executing commands in the shell, all of our output is being returned to the screen, and that's known as standard output. But if we want to output that information to a file, we need to redirect the output from the screen, standard output, to the file. And we do that using the greater than symbol. So what we'll do here is we're going to repeat the command that we've just used, wc-l.pdb. And instead of allowing that output to come to the screen, we're going to use the greater than symbol to redirect the output to a file called lengths.txt, where we can interrogate the information a bit more at our leisure. So let's run that. Again, we don't get any output to screen, but we can use the nanotext that we can either use the nanotext editor or another command, cat, to have a look at the contents of the file. So I'm going to use another command called cat. So this is short for concatenate. And if we use concatenate, it will effectively output the contents of the file to the shell. So if I type cat lengths.txt and hit return, we'll see the output of that wc-l command, which we've redirected to the file. Hang on. I'm just seeing a question in the chat. When I type wc.pdb, it comes out with try wc help for information. So let's try and rerun the command that someone used. So wc, you may have used, from what you've pasted in the chat, you may have pasted 1 instead of L. So let's try that and see if we can reproduce your error. Yeah, so if you've used 1, then you will get a message back saying that it's an illegal option. So what we're using is we're using -L as an option. So it's lowercase l, not 1.
Oh, thank you.
No worries, it's very easy. It's very, very easy to mix those two up. So yes, do be aware of that. So what we've done is we've outputted, we've redirected the output of that command to a file. Now, if we were working with thousands of files, it might not be immediately obvious to us which one is the smallest. So we should sort the output of the lengths.txt file to get our answer. Now, to do that, we can use the sort command. So the sort command takes a file as its argument. So we can sort lengths.txt and we get the output to screen. Now, in this case, it doesn't make a difference to the output, but by default, sort will apply its sort based on characters, so it will do an alphabetic sort. But what we want to do is we want to do a numeric sort, so we're going to use the option -n to make sure that we're sorting in numerically ascending order. So what we've done there is we've sorted the contents of lengths.txt by the number of lines. Now you'll notice that doing that, if we cat the contents of lengths.txt, we haven't changed the contents of the file at all. We've used the file contents as an input to sort, and then the sorted output has been printed to the shell screen. So we're not actually modifying the content of the file. Matthias, you would like to ask a question, I think.
Can we use, like in a compacted way, sort and WC, like typing sort WC to sort out the output without creating an intermediate file?
Yes, and that's what we'll see next. So that's what we would like to. That's our goal, and we can achieve that using a pipe. So what I'd like to show at the moment is that the shell allows us to do these multi-step processes, and there's two ways we can do it. We can create these intermediate files, but the alternative is to use pipes, and we'll show how we can do that in a moment. But let's have a look at the individual pieces first before we do that. Okay, so what we've done there is we've sorted the contents of the file. Now, to get our final answer, the final answer to our question, which molecule is smaller, we want to extract the first line of the sorted contents, so the 9-methane.pdb. And we can do that using the command head. So the command head will output the first n lines of a file. So it takes the option -n, and its argument is 1 if we want to print the first line of a file. So let's try that out, and we get the final answer to our question. Oh, hang on a second, I've skipped a step, so I apologize. So first of all, we sorted the contents of lengths.txt, but let's output that to a second file, sorted lengths.txt. And if we do that, we'll see that we've got another file called sorted lengths.txt, and we can cat the contents of sorted lengths.txt and then extract the first line in the same way that we've just seen. So so what we're doing here is we're using the construct of a pipe to complete a multi-step process in one go. So what I'm doing here is I'm outputting the contents of sorted lengths.txt to the shell. And if I want to use the output of one command as the input to another command, we can use this symbol called a pipe. And that means that the output of the previous command is piped forward into the next command as the input. And the head command will then print the first line of that output, giving us the answer that we're looking for. So there's two ways that we could have done it. We could have typed head -n1 on our sorted lengths file. So that's one way of doing it. So here we're using the head command in the way that we've seen previously. So we're using the head command -n, so print the first line of our file, and that gives us methane.pdb. An alternative way of doing that is to cat the contents of sorted lengths.txt that outputs to the screen, and then we can use a pipe to then extract the first line. And then, as Matthias was saying, we can use the pipe construct to do the whole process on the command line without creating any of those intermediate files. So let's go back and show how we can do that, building it one step at a time. So the first thing that we did was to do a word count of all the PDB files. So we output that to the screen. But let's add our next step using the pipe. So the output of that first command is being fed forward into the next one. And the next thing that we want to do is sort that output so that the smallest number of lines comes first. So we're going to type sort-n. So let's do that. So what we have there is the what we see on the shell is the final output, which is the sorted output from the word count. And then we can add our final step, which is head-n1, where head is going to print the first line of our output. So that should give us the final answer to our question. Okay, so if we do that, we get the final answer to our question, which molecule is smallest, which is methane in this case. Okay, so it'd be useful to stop for a moment and have a go at some of the exercises in the pipes lesson. So let me just bring that up on my screen and share the contents with you. Okay, so okay, so I should now be sharing with you the exercises from the pipes and filters lesson. So the first one that we're looking at is pipe reading comprehension. Can everybody see that?
It is visible, yes.
Yeah.
Okay, that's great. Okay, so the first question that we're looking at is there's a file called animals.txt in the data shell data folder, and it contains the following data. So it's got a list of dates and then an animal next to it. It says what text passes through each of the pipes and the final redirect in the pipeline below. So if you guys could navigate to the data shell data directory and have a go building up this pipe one step at a time. And if you could let me know in the chat, we've got 4 steps there. So if you could tell me what the output is in step 1 to 4, that would be great. And then we'll try it in a moment.
Camilla, can you keep it showing? I think Simone can't see it.
I think it should be. Hang on, I think it's showing.
Simone, can you speak up and tell us what is it that you want showed? What is it that you can't see? Is it the text of the exercise?
Oh, okay, no, sorry. No, I can see it because actually I'm running Zoom on the website and sometimes have some problem. So no, now I can see it.
Okay, is this good enough for you to be able to do the exercise?
Yep, yes.
Okay, good.
Thanks.
Okay, so let's have a look at this pipe in this exercise. So it says that we need to be in the data directory. So I'm going to navigate to that directory from where I currently am. So I'm going to use the pwd command to check where I am. And I'm in the molecules directory, but I need to be in data, which is one level above. So I'm going to type cd ... followed by data. If I hit return and then pwd and check where I am, I'm in the data directory, and let's check out what's in there. So as expected, there's this animals.txt file. So let's have a look at what this pipe achieves. So the first step is to cat the animals.txt file. That's our first command. So what cat does, concatenate, is that
you need to swap to your terminal.
Thanks, Doug. Okay, so let me just repeat that. So I'm in the molecules directory, but I want to be in data, which is one level above in data shell. So I'm going to type cd ... data to take me there. Check where I am using pwd, and then list the contents to find what I need. So I want the animals.txt file to check out what this pipe does. So I'm going to use cat as my first command, which is going to print the contents of that file to the shell screen. So let's do that. Cat animals.txt. And it reproduces what we see in the exercise. So what that does is it prints the contents to the screen. So the next step that we want to do is you want to truncate the file and just take the first 5 lines of the content. So we're going to use head. So head-n 5 is going to give us the first 5 lines of the file. Okay, so we can build up the next step in our pipeline again by using tail. So tail is the opposite of head. So head allows us to extract a certain number of lines at the top of a file. Head is its opposite number, so it allows us to get the contents at the bottom of a file. So head-n, and this time we want the last 3 lines of the file. So that's going to give us, so we've taken the first 5 lines, and then we've got the last 3 lines of that 5 lines. Okay, and then the final step is this reverse sort. So we're using the sort command, but we're doing it in reverse order. So what that's giving us is it's giving us the latest date first. So that's a good way of interrogating what a pipe does. We can try each step at a time and look at how each part of the pipe modifies the output of the last. And in the exercise, the final step is to redirect the output to a file. So we've seen that we can use this greater than symbol to redirect output from the screen into a file so that we can have a look at it later. So let's do that now. So we've got final.txt. And if we have a check, we can see that our final.txt file is there as we expect. Okay. Okay, so I'm going to move on to the next episode because we've got a lot of material to cover. So we've got 2 more really key lessons to go through, which is loops and shell scripts. So I'm going to move on to them now, but if we have time to do more exercises, I'll come back at the end of the session and we can try out some more exercises together. So I'm going to clear the output of my shell screen. So we've got a clean page to work from. For the loops episode, we need to be in the data shell creatures folder. So let's check where we are. I'm in data. I want to go to creatures, which is not in the data directory. So we need to go 1 level up. So I'm going to do cd ... and creatures is in data shell. So we're going to do cd creatures. Now,
did everyone manage to navigate to the creatures folder just now? Green ticks showing up.
Okay, so everybody looks like they've managed to get there. So in this section, what we're going to look at is how to apply commands repeatedly to a series of files. Now, we've encountered wildcards in the last hour or so, but sometimes what we'll see is that wildcards aren't powerful enough to do what we need to in terms of repeating operations on a set of files. So let's have a quick look at that. So we've just met the head command, which we've seen allows us to print the first n lines of a file, and we can specify the number of lines we're interested in. So what I'm going to do is I'm going to print the first 5 lines of this basilisk file, which is in this folder. So we've got a file. Actually, let's just pause for a second and have a look at what's in here. So we've got basilisk, minotaur, and unicorn.dat in this folder. And what I want to do is print the first 5 lines of the unicorn file. So I'm going to type head-n5 followed by unicorn.dat. And when I do that, I can see that we've got a uniform file structure. So we've got the common name, the classification, and so on. Now, what if I wanted to then print the last line of this file, for example? So let's say I want to get this genetic code at the bottom. So what I can do is I can do head-n5, and then I can follow that up using a pipe with tail-n1. So we've printed the first 5 lines, and then we're going to print the last line of that first 5 lines using tail. And that's going to give us that string of genetic code there. Now, we've done that operation on one file, unicorn.dat, but what if we wanted to repeat that for all of the files in that folder? So, for example, I might be interested in getting the classification of each of these creatures. So what I could do then is, instead of doing head-n5, unicorn.dat, I could do head-n5 followed by tail-n, hang on, 1, 2, 3, 4, I think. So if I wanted the classification, I could do head-n2 to give us the first 2 lines, and then tail-n1, which will give us the classification line. So I've done it for unicorn.dat, but what if I want to do it for all of these dat files? So based on what we've learned so far, an intuitive answer might be to try head-n2 star.dat. Okay, so let's see what happens when we do that. So when we do that, we might have thought that we would get the classification of each of the files in that folder, but that's not what's actually happened. What's happened is that we've printed the first 2 lines of each of the 3 files, head-n2. Okay, so we can see that first part of our pipe. And then if we add the second element of the pipe, tail-n1, we've actually printed the final line of the whole output from the first part of the pipe, which is not what we want to achieve. So although wildcards are really powerful, to repeat operations on files, sometimes we need to use loops. So let's have a look at how to construct a loop and print out the classification of each of these files in turn. So let me just check which creatures we've got. So if we want to print out the classification of each of these creatures, we need to use a loop. So we're going to construct our loop using the following structure. So we're going to type for file name in, and then we're going to list each of the files. So I'm going to type basilisk.dat, minotaur.dat, and unicorn.dat. So what I've done here is I've listed each of the files individually to start off with. Now, when I hit return, we're going to see something that we haven't seen before. The shell prompt has changed from the $, which we've seen a lot before, which means anticipating input. It's changed to the greater than sign, and that means that we haven't finished inputting our command into the shell. So we're going to carry on. So the next element of the loop is to type do, and again return. And then the body of the loop, so this is what's coming now, is the command that we want to apply to each file in this file list. So I want to repeat this operation, head-n2 star.dat, pipe tail-n1. Hang on, no I don't. I want to type head-n2 and I want to apply that to the each of the file names that are listed here. So what we're using here is known as the loop variable. So the loop variable is file name. So file name, for each iteration of the loop, this variable file name will take on the value of the file name listed here. So we designate that using a $sign. So the final part to close off the loop is to put in a done statement, and that gives us a complete loop. So what we've got is we've got on the first line, we've got our sort of for statement where we're saying for file name in basilisk.dat, minotaur.dat, unicorn.dat, and then we've got this, the do statement, and then the body of the loop, which is what we're going to apply to each file name, and then done to indicate that the loop is closed. Okay, so let's run that and see what happens. Okay, so let's dissect this a little bit. So this loop is going to go through 3 iterations. So what will happen is that we will first take the file name basilisk.dat, then minotaur.dat, and then unicorn.dat. And for in each case, the loop variable file name takes the value of that file name, and we run the commands in the body of the loop on that file. And the output that we get reflects that. So the first output that we get is the classification of the basilisk, then the minotaur, and then the unicorn. So it's worth noting a couple of things about the construction of loops before we move on. So the first one is that loop variable file name, we can call it anything we like. We could have called it for x in basilisk.dat, minotaur.dat, unicorn.dat, and we would have got exactly the same result. So that's the first thing to notice. Hang on. So yeah, we could have used any variable name instead of file name. So we could have used X, we could have used temperature, as you'll see in the notes. But the important thing is to make sure that whatever name you use for the loop variable is informative. Now, there's another way that we can modify. There's another way that we can modify this loop very slightly. So in the first example of running this loop, we've listed each of the DAT files that we want to apply the commands to explicitly, but that's not very flexible. And this is where we can make use of wildcards and loops together. So an alternative way of achieving the same result here would be to type for file name in star.dat. And in this case, we're going to apply our loop to every file name which matches the pattern .dat in that folder. So we're going to do for file name in .dat do, and then head -n to $file name -tail, sorry, tail -n1, and then done. And yes, the other bit of information that I wanted to mention was that you'll notice that we've indented the body of the loop here, and that's convention to make the loop a little bit more readable for us. Okay, so let's have a go at running this. So when we run the loop this time, we get exactly the same output, but we've written our loop in a much more flexible way this time using star.dat. Okay, so can I just do a quick check on how everyone's doing? Has everybody managed to follow along in writing a loop? If you haven't, please put up a red no, and I'll go through running the loop one more time, very happy to.
So we are helping Emil in the chat a bit, but looks like and Simone can use the indicators because he's using a web browser version of Zoom, but looks like most of the people managed to
Okay, that's great.
get here.
Okay, let me just check where I'm up to. So that gives us an overview of using loops with wildcards together. Now, there's a lot more material in the loops episode, but I'm going to skip a lot of it. So I think we've covered the absolute core of what you need to know in terms of loops there. So we've shown how to, what we want to get across is how do you run a command on multiple files in sequence, and we achieve that using a loop. And I'm going to skip the rest of the episode because it's a consolidation of that process. And I'm going to move on to looking at shell scripts because I think this is the most powerful element of working with shell and will be the most useful to you. So right at the beginning of the session, we talked about our aim being to automate those repetitive tasks. Now, loops are really useful because they allow us to do those tasks very quickly. So, you know, you'll see that the classification of, we managed to get the classification of those creatures very quickly. And it's much more quickly than if we'd had to point and click and open those files and copy the text from them. But there's a potential issue with the way we've been working so far. We've been typing everything into the shell, and it's not necessarily particularly reusable because we don't have, you know, we'd have to keep records of exactly what we're typing into the shell. And what we want to do is to be able to save these small programs that we've been using so that we can reuse them. And we also want to look at how we can make them very flexible so that we can use them in different ways on different sets of files and so on. So let's have a look at how we might do that. So for the next section, we're going to go back to the molecules directory. So I'm going to use the // shorthand to go back up into the data shell directory, and then I'm going to use cd molecules to navigate into the molecules directory. So what we've done so far is to type all the commands that we've been using directly into the shell. So what I'm going to do now, what we're going to move on to do now is saving those commands in a text file and then running the contents of the text file as a script. So we're going to use nano. Let's use nano to create a file called middle.sh. Now it's convention to use with the file extension .sh for script files, for bash script files. So that's what we use here. So nano middle.sh. So as soon as we run that, nano takes over our terminal, as we've seen before. And what we're going to do is going to write the contents of our small program into this text file. So what I'd like to do for this simple program is print the first 15 lines of the octane.pdb file and then print the last 5 lines of those 15 lines. So we can do that two-step process using a pipe. So let's get started and try that. So we're going to type head-n 15 octane.pdb, then pipe, and then tail-n5. So that's the command that I'd like to run. Once I've inputted it into nano, I'm going to do Control X to exit, Y for yes, then return to confirm the name of the script that I'd like to use, which is middle.sh. So once you've got to that point, if you could, I'm going to just clear the, once you've got to that point, if you could give me a green tick to let me know where you are and that you've created the middle.sh file.
Maybe show the contents of the file so people can know what to type. That's great. Thank you.
What do you click after you've put file name to write middle.sh?
Just, I think you type return to execute. So
Okay.
you'd execute it as a command in the same way that you've executed the others.
Yeah, got it. Thank you.
Okay, so I'm just waiting for a couple more people to create their middle.sh file. Okay, I think we're just waiting for one or two more people. So just to recap, once you've added the contents to Nano, we are going to type Control X. Ooh, hang on. Control X, and then confirm the file name. So Control X, yes, and then confirm, enter to confirm the file name. Okay, so if we have a look at the contents of molecules, sorry, I typed ls-l there, and ls-f. What we want to do in our command is to print the first 15 lines and then the last 5 lines of those 15 lines. So I'm going to do it on the command line before we run the script that we've just written. So let's do it on the command line first. So head-n15 octane.pdb. So that's going to print the first 15 lines of octane.pdb. Then I want to add the next step in my pipeline, which is to print the last 5 lines. So I'm going to add the next element to the pipe after the pipe, tail-n5. So once I do that, I get my output to screen, which is the last 5 lines of the 15 lines. So the middle lines of the file, effectively. So that's why I've chosen the name middle.sh, because we're pulling out some of the middle lines of the file. Okay, so we've typed exactly the same command into our text file, middle.sh. Now, we can run that script, the commands in that file, by typing bash middle.sh. Now, if we do that, you see that we get exactly the same output as though as we do when we run the commands directly on the command line. But the advantage of having the text file is that it's saved for us to refer to anytime that we like. The other main benefit of working this way is that we can modify our code to make it extremely flexible. So let's have a look at how we might do that. So in this current command, we've just operated on the file octane.pdb by itself. But what if I want to be flexible and be able to run this command on any PDB file that I specify? So we can do that using arguments. So I'm going to open up my middle.sh scripts in nano. So I'm going to type nano middle.sh and then return. The contents of that file is head-n15 octane.pdb, type tail-n5 at the moment. But what we're going to do is we're going to replace octane.pdb with $1. Now, $1 is a symbol for the first argument of the command line. So you'll notice that when we ran our script, we typed bash middle.sh. And when we looked at the anatomy of Unix commands before, we break it down into the command and the arguments. So we are going to specify some arguments after middle.sh, which are going to be utilized by the main part of the program here. So $1 stands for the first command line argument of middle.sh. So and we are putting the $1 in quotes in case we encounter a file name with spaces, but perhaps more on that later if we have questions or further discussion. So once I've modified that by removing octane.pdb and putting $1, I can type Control X. It says, do I want to save changes? Yes, I want to save my changes. Confirm the file name, middle.sh. So return to confirm. And let's have a look at running that again. So bash middle.sh. Now this time, the PDB file that we want to operate on isn't written into our file. We need to specify it as an argument on the command line. So we're going to type bash middle.sh, and then we're going to type the name of the file that we want to operate on. And this time I'm going to type octane.pdb. So when we do that, you'll notice that now we've had exactly the same output as we got the last two times we've run this command. But this time our script is written in an incredibly flexible way. So we, instead of using octane next time, if you want to, we can try a different file, for example, pentane. So we can type bash middle.sh pentane.pdb. And this time we get completely different output. You'll notice this is different to here. So we're pulling out the middle lines of the pentane.pdb file. Okay, so can I just do a quick check with everyone? Have you modified the contents of middle.sh to include $1, which is our command line argument? Okay, so that's looking good. It looks like most people have done that. Okay, brilliant. So in that single modification to the script, we went from a command which did one thing on one file to something which is a little bit more flexible. Okay, now I wonder if we could make this script even more flexible. So let's have another look at the file contents and see what we can do to make this even more flexible for us to use. Okay, so in terms of things we can change in this script, there are two other things that we can change. So we can change the number of lines that are extracted by head, and we can change the number of lines which are extracted by tail. So let's change these to parameters as well, not just the file name. So what we can do here is replace 15 with quote $2. That will be our second command line argument. So we're not just restricted to one. And we're going to replace the 5 with a third command line argument, which is $3. Okay, so once you've modified the script that way, you can use Control X to exit, Y for yes to save the changes, and then return to confirm that we want to save the file as middle.sh. And then we're back to the command line. And this time, when we run the script, we're going to provide 3 arguments, not just one. So we're going to provide the file name, we're going to provide the number of lines extracted by head, and the number of lines extracted by tail. So I'm going to type bash middle.sh octane.pdb. Instead of using 15 lines, I'm going to use 10. I'm going to extract the top 10 lines using head, and then in tail, I'm going to extract the bottom 2 lines. Okay, so let's try that. So this time we've had completely different output again. So we've used the octane.pdb file, but we've extracted the first 10 lines and then the last 2 lines using tail. So our output is just 2 lines in length. Okay, so how's everybody doing? You just give me a green tick to let me know you're at the same point.
Susanna asked if they can see the text in the nano file again, I think.
Yeah. Okay, so once you've got to that point, one of the last things to look at that's useful to look at is perhaps to think about a scenario that we might encounter every day when we're doing our research. So let's navigate up to the data shell directory, and we'd like to navigate into the North Pacific Gyre folder. So if we cd North Pacific Gyre. Okay, so let's have a look at the contents of this folder. So there's a subfolder called 2012 0703. So let's go into that folder, 2012 0703, and check what's in there. Okay, so what we're going to do in this section is to write a small script that would allow us to apply an analysis to every file in this folder. So if you type ls-f to see the contents of this folder, what you can see is there are some text files which are results from an assay machine ending in A and B and Z. And then there's two executables in here. There's goodiff and goostats. And I want you to imagine that goostats is a command that might do a useful statistical analysis for you. And what we're going to look at now is how could we combine all of the elements that we've used so far, so wildcard, loops, and storing our commands in a script to allow us to run that analysis on every file in this folder very quickly. So to do that, we're going to create a text file called do-stats. So if you type nano do-stats.sh, okay, and we're going to start constructing a loop to do the analysis on these files. So we're going to pretend that in this case, we just want to do our analysis on files that end in a.text. So what we're going to say is for data file in star a.text, and then do. I always prefer to write do and done together. So I remember that each of those elements needs to be there. So our first line is for data file in, and then a list of files. And then we've got these opening and closing statements, which are do and done. And then I like to write the body of the loop last. So what we're going to do is for each iteration through the loop, I want to know which file I'm working on. So I'm going to introduce you to another command that we've not met yet, which is echo, which is effectively printing something to the screen. So we're going to do echo and then data file. So that's going to allow us to keep track of which file is being processed at any one time. The next line that we're going to do is we want to run that program goostats that we saw on each of the files, each of the text files, so each data file that we encounter. So let's do, so we're going to type bash goostats and then $data file. Now, we don't want to just print the output of goostats to the shell, we want to save it. So what we're going to do is going to redirect the output of goostats to a new file, and we want to preserve a significant portion of the original file name, but we want to going to add a prefix, and the way that we're going to do that is by typing stats underscore data file. Okay. So this gives us a basic loop, which is going to allow us to run the goostats data file on each of the text files, starting with A in our directory. So let's give that a try. So Control Y and then save. So let's give it a go and hope that there's no mistakes in there, but if there are, we'll address them. So we've got bash doStats.sh, and when we execute that, what we see is each of the file names is printed to the shell because we wrote that into our loop using that echo statement. And if we list the contents of our directory, you'll see that for each iteration, we've generated a new file, which is the output of the statistics analysis program. So it's time for you to have a go. So I'm going to pull up doStats again, so you can transcribe that and have a go. And once you've transcribed it and run it, if you could give me a green tick, and we'll use the last 10 minutes to do some exercises together. So, oh, sorry guys, I just clear all the output, and then once you've written a doStats script and run it, just give me a green tick, and then we'll make some last remarks on shell scripts, and then go back to doing some exercises. So to recap, we've got our loop structure here. So we've got our loop variable data file. So when we run the script, what's happening is we're using the wildcard *a.text to identify all text files that end in a.text in the current directory. So that wildcard gets expanded and matched against the contents of the folder. Then for every file ending in a.text, as we go through each iteration of the loop, the file name will be echoed to the shell as a result of using this echo command. Then we're going to run the goostats program using the data file as an input. and then we are redirecting. So if we ran this without the greater than sign and the redirect, the output of the statistical analysis will just get dumped to the screen, which isn't very useful if we're pursuing a reproducible analysis. So what we're doing here is redirecting the output to a text file, and the text file is stats_data file. So instead of, so what we're saying is we want to keep most of the file name the same, but we want to add a prefix, so stats_, so that we know where the results are saved. Okay, so there's a few people who haven't given me a green tick. Does anybody have any specific questions they need help with, or like me to go over anything? Okay, so I'm going to assume that everyone's okay. But if you're not and want us to hang on, just please write in the chat. So the last thing that I want to mention before we move on is that it's generally a good idea to document your code as you write it. So we can add comments to our scripts using the hash symbol. The hash symbol indicates, or pound symbol, indicates a comment. So we can write comments here that won't be executed or displayed when we run the script. So it's useful to give an explanation of what's happening here. So, so it's useful to say what the script does and also how to use it. So let's say perform statistical analysis on every text file ending with a.text, and then usage would be hash do stats .sh. Okay. So, and then as you can see, if we run that again, the commands have no, oh, hang on. The commands have no impact on, the comments have no impact on the way the scripts run. Can anyone tell me what I've done wrong in inverted commas here? So the first time we ran the script, the output that we produced was this set of files here, but this time we've got another set of output here. So can anyone tell me what I've done there? Yeah, so I've run my statistical analysis on the output of my statistical analysis. So yes, beware. Okay, so we've got about 5 to 10 minutes now. So I think it'd be useful to go back and revisit some of the exercises from the loops lesson and from the shell script lesson. So I'm just going to stop sharing the terminal with you and pull up the exercises. Okay, so let's start off with the first exercise, limiting sets of files. So this is the link to the lesson, and we're looking for the exercise, limiting sets of files. So there's 3 exercises here, limiting sets of files, saving to a file in a loop part 1, and then saving to a file in a loop part 2. Okay, so if you have a look at limiting sets of files, I believe I'm sharing with you now. Let me know if you can't see anything. So this exercise is showing us the example of a loop. So what would be the output of running the following loop in the data shell molecules directory? So the loop is for file name in C star, do list file name, done. So there's 4 options. No files would be listed. All files would be listed. Only Cubane, Octane, and Pentane are listed, or only Cubane is listed. If you could vote in the chat and let me know what you think, whether it's 1, 2, 3, or 4, and then we'll try it together. Okay, so we've got lots of votes for number 4. Okay, so let's give it a go. I'm going to switch back to sharing my terminal with you. So when we look at the next questions, I'm just going to read them to you. So if you could follow along on your copy of the course notes, that would be really helpful, so I can keep sharing the terminal. Okay, so I believe I'm sharing my terminal now, so I just want to check where I am because I always forget. So I'm in that folder North Pacific Gyre, which is not where I need to be. So I want to go back up several levels. So I want to go back up to data shell. So I need to do cd .. to go up 2 levels, check where I am in data shell, and then I want to go into the molecules directory and list what's there. So I think that loop said what would happen if we looped over files which were C star and then listed them. So I'm just going to do that from memory. So please correct me if I'm wrong. I think it was for file name in C star. Then we hit return and we're going to put in those elements of our loop. So we put in do, and then we're going to write the body, which is list $file name, and then done. So I think everyone voted for 4, which was that this is just going to print out Cubane. So let's have a look, see what happens. Yep, so that's what happens. The wildcard C star gets expanded and matched against the contents of this directory. The only thing beginning with C here is Cubane, so that's what we get back in our output. Okay, so let's have a look at the next question. I'll just read it to you, but if you guys could follow along on the actual course notes. Okay, so the next one is another example of a loop, and it says, in the data shell molecules directory, what's the effect of the following loop? So the loop is for alkanes in star.pdb, do echo $alkanes, cat $alkanes, greater than symbol, alkanes.pdb, and then done. So we've got 4 options there. It says it's going to print each of those file names, Cubane, ethane, methane, octane, pentane, propane, and the text from propane.pdb will be saved to a file called alkanes.pdb. It prints Cubane, ethane, and methane, and the text from all 3 files will be concatenated and saved to a file called alkanes.pdb. Okay. Prints Cubane, ethane, methane, octane, pentane, and the text from propane will be saved to a file called alkanes.pdb. Okay, so do you guys want to vote in the chat? Let me know which one you think is the right answer. There's no rush, so please take your time. So we've got 1 person's voting for number 1. What do other people think? Okay, so we've got one person voting for, we've got a couple of votes for 1 and a couple of votes for 4. So let's look closely at those. So 4 is none of the above. So let's break it down and then actually do it. So for alkanes in star.pdb, that's saying, okay, I think we've complicated it by, oh no, we haven't. I was going to say I've created some more PDB files, but I deleted them, so panic over. Okay, sorry about that. Okay, so for alkanes in star.pdb, what PDB is going to expand to a list of all PDB files in that folder, and we're going to loop over each PDB file. Then we're going to, so as we do that, alkanes is going to take the value of the file name. So we're going to echo the file name to the shell. And then we're going to, the cat command is going to be invoked. So we're going to cat the file, and the output is going to be redirected to an alkanes.pdb file. But an important point to mention about, I suppose we haven't gone into this too much so far. So when we use the greater than symbol to redirect output to a file, that is a destructive command in the sense that if that file already exists in the folder, it will be overwritten. So every time this loop is executed, the contents of the file is going to be catted and redirected to a PDB file. But each time, for each iteration of the loop, that file is going to be overwritten. So what we're going to get is what we would expect is the output from 1. So let's quickly give it a go. So for alkanes in .pdb, do hang on, sorry, got the second line, echo alkanes, cat $alkanes. Okay, so what we've got there is we've had the file name of each PDB file printed, 1 file name per iteration. And let's have a look at the contents of alkanes.pdb to see what it contains. So it looks like it only contains the output from propane. And the reason for that is that propane will be the last PDB file that's listed. And so it'll be the final file to be processed in the loop. And as I said, that greater than symbol is destructive in the sense that it overrides any existing file. So that alkanes.pdb file will be overwritten on every iteration of the loop. Now, if we did want to concatenate the contents of all of those PDB files into 1 file, the second exercise is going to show us how to do that. I've kind of given away the answer already, but let's have a look at it. So let's have a look at saving to a file in a loop part 2. So what would be the output of the following loop? So for data file in .pdb, do cat data file, and we're seeing an element here that we've not seen before. So we've talked about the greater than symbol being used to redirect output to a file, and I've said that that's destructive because it overrides any existing file of the same name. But using 2 greater than symbols doesn't do that. It will append to an existing file. So if the hang on a second. So if the file it doesn't exist, it will create it. And if it already exists, it will concatenate to the file. So let's give it a go. Sorry, not concatenate, append to the existing file. So let's have a go. We don't have a file called all.pdb in this folder. So we're going to type for data file in .pdb. And then we're going to type cat $data file, and then we're going to use 2 greater than symbols this time. So this indicates that we want to append the contents to the all.pdb file, not override it on each iteration. So this time we didn't include an echo statement to allow us to track what was going on. So our loop's just being executed without giving us any output to the shell, but we can check the contents of all.pdb using nano. So if we type nano all.pdb, we can now see, if we scroll down, that we've got the contents of all of the molecules being appended together. So we can, if I exit nano, we can come out of there. Alex, how are we doing for time? Is it okay if I carry on, or?
I think it's probably time to finish. So I don't know how people are feeling, but if you have, I don't know, one quick last exercise, and then we probably have to wrap up for the morning.
Okay, I think it'd be just good if we have a look at one exercise from the shell scripts episode. That'd be really
Shall we have a
useful.
vote to ask?
Yeah, sure,
Do
absolutely.
it the democratic way.
Yeah, sure. It's absolutely fine.
See how people are feeling. Do they want one last exercise, or they're?
Yes, that's fine.
No is a valid answer as well.
I'm just going to turn off my video for a second because I'm having a technical problem with my monitor. So I'll come and find out the answer in a second.
We've got one green tick. Okay, two or more showing up. Okay, someone seems to be tired. So while we are waiting for Camille to come back, can you hear me, or have I dropped? Okay, so while we are waiting for Camilla to come back and make a decision whether we are going to do one last exercise or not, just wanted to kind of give you a, I don't know, higher level overview of Shell. So you might be thinking, why are we learning all this? Why is this useful? Where you can, in modern operating systems, you can do most of these things in a graphical interface or in a point and click fashion. So it is good to know these things as you start writing more scripts yourself, either shell scripts or Python scripts or R scripts or any programs in other programming languages where you will need the shell in order to run those programs. Or if you want to run those programs on multiple files, then a graphical interface is not going to be helpful to you. Sometimes also you might have to remotely to connect to a machine, in which case you might just get the terminal window available to yourself. So that's why it's good to know how to navigate through the shell and to find your way through all these different files. Or also if you inherit a program from someone else that only runs in a shell, you would need to know these things. So that's why we are teaching you this. And also, if you start using version control a bit more, again, this is something that you will use from the shell. Even though modern programming environments often incorporate version control or running programs from within the graphical interface itself, it's good to know the principles behind the shell and that you can always do things from the shell as well. Camilla, are you back?
Yes.
Okay, so people who are tired are free to go now and have a break. And I suggest that we come back at 40 minutes, 40 minutes till 2. Okay, and then we'll just carry on for a minute or two to finish off the last exercise. Okay, so back at 22, sorry, not 40 minutes to 2, 20 minutes to 2. So 1:40 is when we are back. So 1 hour from now. Okay, over to Camilla.
Okay, so I've chosen an easy one for our final, well, not an easy one. None of this is easy, but one which doesn't involve you writing a whole script. So one of the shorter ones, that's probably more correct to say. Hang on. Okay, so if we have a look at the question, variables in shell scripts. So we're looking in the molecules directory. And the question says, in the molecules directory, imagine you have a shell script called script.sh containing the following commands. And the command, there's two commands in the script. So it's head-n $2 $1 and tail-n $3 $1. So that's the contents of the script. So it's two statements on two different lines. And it says, while you're in the molecules directory, you type the following command: bash script.sh star.pdb 1. So it says, which of the outputs would you expect to see? All of the lines between the first and last lines of each file ending in .pdb in the molecules directory, the first and last line of each file ending in .pdb in the molecules directory, the first and last line of each file in the molecules directory, an error because of the quotes around .pdb. So what do you guys think? There's 4 options there. If you guys could vote in the chat. And I think it's worth mentioning that if you want to work out the answer to this question, you guys could head over to the molecules directory and test this out yourself and see what happens with those different arguments. So it's telling us that we've got this script.sh, and I think we've only just covered this material. So we're running the script.sh by typing bash script.sh, and then we've got these 3 arguments after the script. So we've got star.pdb and then 1 and 1. So the first argument .pdb is what files the head and tail commands are going to operate on. And then the subsequent arguments 1 and 1 are the number of lines we're going to extract. So if you guys could vote for me and tell me which one will you go for, 1 to 4. So this exercise is in shell scripts. And it's the one called variables in shell scripts. So I think we've got 1 vote for number 1. Okay, we've got another vote for number 2. Okay, 2 votes for number 2 so far. Okay, so let's give it a go. So I'm going to head over to, oh, I'm already in the molecules directory, which is good. Okay, so let's try it. So I'm going to create the file script.sh. So nanoscript.sh head-n $2 $1 tail-n $3 $1. Okay, so Control X, Y to save, return to confirm, and let's run this script then and see what happens. So bash script.sh star.pdb and then 1 1, and then in the exercise example this was in quotes, so let's do exactly the same. So bash script.sh. Okay, so what we appear to be getting, let me just confirm and open one of the files. So let me open propane.pdb to have a look at it. So the first line is this compound line and the last line is the end line. So it looks like what we're getting is, first of all, it prints us the first line of each file, and then it prints us the last line of each file. So it would be 2 would be the correct answer in this case. Okay, so everyone who voted 2, yes, that's correct. Okay, so Alex, back over to you.
Great, thanks very much, Camilla, for this great shell intro. So we are going to break for lunch now. I'll share my screen for a second, because we want to ask you, just before you disappear for lunch, on line 200.